More importantly, can everyone read my handwriting? Does everyone know what that says? Okay, good. I mean, if there are math AI students here, you are free to ask questions. I mean, Parya, what is wrong with you? I'm not changing this. But if there are AI people that want to ask AI questions, I can try my best to answer it. But I'm not. There's stuff in the AI syllabus I don't really know. Okay, I was just about to say that. So I need. Okay, first of all, I'm going to run this session for roughly 2 hours. Let's see how long I lasted if I actually my brain is still functioning after 2 hours of math. But are any of you going to stay for the full 2 hours? If so, I want a volunteer that will remind me to drink water every 20 minutes. Okay, great. So just like set a timer for 20 minutes at a time, and whenever it goes off, just remind me to take a sip of water. Thank you. And Harya, are you gonna be staying around, or do you want someone to take over the questions stuff? Okay, so in that case, I want one more volunteer, someone else, to basically take up what Parya is doing. So when people post questions, uh, you basically track the questions that are being posted and the ones that I haven't done so far. So you essentially just right click the message and copy the message link whenever people post questions, and then whenever I pull a question, you can remove it from the list. Okay, great. Thank you so much. So Concarne is giving me water reminders. I'm cool. Will give me questions. Great. Thank you so much. Okay, here's how this session is going to work. I will just be going through the questions that are in the chat, and this will be in the M25 revision stage channel. So not the Math AA channel. I will not be checking that. Post all your questions to the stage channel text thing window on the side, and I will just go through questions one by one. The questions can be anything to do with Math AA. Like, it doesn't have to be a test or exam type question. It can just be a general, conceptual, whatever. And I'll try and explain it to the best of my ability. And yeah, that is basically it. Okay, let's get started. First of all, do you guys want me to explain the thing that I asked in Math AA, or should I just get to your questions? Okay, let me grab my own question. Hold on. Okay. Let's start with this. Okay, so what I asked is there's 6 students that are sitting around a circular table to play a game. Circular is important. I said circular because I wanted to say that rotational like configurations that can be rotated into each other are actually the same configuration. So it doesn't matter like which person is sitting at the bottom of the table versus at the front or the back of the table. You can flip the table around, like rotate it, and it's the same configuration. That's what that means. Okay. There are 3 of them wearing red shirts and 3 wearing green shirts. The rules require that red and green alternate going around the table. How many ways can the students sit to play the game? Okay. I'm gonna do what I think the calculation that most of you guys did, which is, so okay, there's a circular table, right? There's 3 red people, and 3 green people, right? Now, where the reds and greens are fixed, right? But this is not the only, like, let's say that the rotational configuration actually does matter, right? We know it doesn't for the question, but if it does, then this is not the only option, right? There's also, we could have green at the top. So we could have the configuration look like this, right? In each case, the configurations of reds and greens are fixed, right? There's 3 greens in specific locations, and there's 3 reds in specific locations. Now, within each individual group of 3, there can be any permutation, right? So for each of these individually, so for this one, we have 3 factorial for the greens. All right, let's write it in green actually. Times 3 factorial for the reds. And that's it. That's all the configurations that look like this. And, this is also a valid configuration. So same thing applies there. So if you add these two up, this and this should give you 72 in total, if rotational symmetry wasn't applicable. But one thing that I tried to specify is that if you can rotate the table and get an existing configuration, it is the same one. Because there's 6 people around the table, each configuration has 6 copies in this count. So in order to not overcount by a factor of 6, you divide by 6. So actually, the answer here is 12. Okay. Is everyone happy? Is that question finally off your guys' mind? Okay, great. Now let's start with the actual questions. Okay, let's put this here. Okay, let's actually start with this now. Actually, let me do something to save space. Let's move you up here. Okay. A very bouncy ball is dropped from a height of 2 meters. After each bounce on the floor, it rebounds to 4/5 of its previous height. Okay, there's a bunch of parts. I am cool. Did you have a specific part you wanted me to do, or just work through all of it? D part, okay. Time t that it takes for the ball to drop a distance s on each bounce is given by, okay. Each ball takes the same time to as it is coming down. Okay. So I can do something that people ask from the physics Q&As, which is that if there are people here who aren't the person asking the question who want to try and attempt it, I can give you guys a minute to try it out. Or at least, come up with a strategy or like a method to tackle this one. I think I have an idea, but I'll give you a minute. If you have an idea or you want to post an answer or something, uh use spoilers. So if you don't know how to spoiler stuff, you use the vertical bar or pipe character to hide whatever text is in between. Really? I'm not that old. Okay. Any ideas? Or should I just start? Okay, so when I look at this question, uh, especially with this and looking at all the previous parts, this is going to be some sort of geometric series, right? And the way I'm thinking about this is on each bounce, the height that it goes to goes down, and what that means is the time taken over each bounce also goes down, and it'll go down in a geometric way. And so the total time will be a geometric series, right? Because you're summing each term in a geometric sequence. So you know that, like, okay, let's say S of 0 is like the first height, which is what it's bounced from. So this will be like 2 meters. Then S1 will be whatever 4/5 of that is. And so on, right? Like, I don't have to write the rest of this out. But this is one sequence. And you know that it also says for each bounce, the ball takes the same time going up as it does coming down. So it'll actually be 2 times this value for everything after 0. Right? Does that kind of make sense? So the so let's think about the time now, right? So the time taken for this one, well, okay, let's rearrange this because we actually want to solve for the time. So what was that? S over 5. That looks like 5 over 5. Why? Okay, that kind of looks like S over 5, right? So the time taken for this will be root 2 over 5, right? But for this one will be, whatever, 4/5 times whatever's in here, square root. But it spends this time going up and coming down. So what that means is I have to multiply this by 2, right? And then for the next one, the next time will be, 4/5 squared times 2 over 5 under the root times 2 again because it has to go up and come down. So what do you notice about the sequence of times over the jumps? Right? There's a common factor apart from this, right? Like over here, there's no times 2. But from here onwards, you have a common factor of square root of 4 over 5, right? Or I guess I can write this as 2 over root 5 or something. No, I'll just write 4 over 5. I cannot write a 5 at all. Right? So you have your R and you can just take, you can probably just take this as your first term and then add this at the end, right? I should write T0, T1, T2. So from here, it's just applying the formula, which is your sum to infinity geometric series formula. This, of course, is less than 1, so you know that it'll converge as you go to infinity, and that's basically it. I'm guessing you need a calculator for this because there's a square root in there, so I don't think I'm gonna. I don't know where my calculator is, but it should be there on your formula booklet somewhere. Where is it in your formula booklet, actually? Sequences and series. Sequences and... Oh, there we go. Yeah, so here you have your R. You can probably just take this as your U1 and then just add this on at the end. Right? Is that clear to everyone? Did I get it wrong? Why does that... That's what I said, right? So from everything after the 2 meters, you take that as your geometric series. And then at the end, you just add the 2 meter time once. There's no times 2 here, right? Which is why I said start from T1 and not T0. Otherwise, it's a bit confusing because it's not. Yeah. Okay, is that clear to everyone? And I'm probably going to do this sort of hand wavy thing at the end for whenever there's calculations, because you guys, I'm going to trust that you guys know how to use a calculator. The times 2 is to count the up and down. Yes. Actually, I'll draw that explicitly. This is going up and then going down. So that's where the times 2 is coming from. So I don't know what the answer is. It's something with your calculator. But something I want to emphasize is that most of the marks in your math exam is not from the final answer, right? It's from doing all of this crap. So at the end, you just plug everything in and get some answer, which I don't know where my calculator is, so I'm not going to do that. But that'll just come with practice, and whenever you guys do your revision with past papers and stuff. Oh yes, water, thank you. But this is the method, and this is the line of thinking, and that's the most important thing for you guys to take in with you in the exam. Okay, I'm going to move on to the next question. If people have oopsies. Yeah, got it, thank you. If people have questions on Like if you still have questions about this, just ping me and I'll take a look. Otherwise, I'm gonna just move on. Okay, let's put a question here. Okay, that's a large screenshot. Okay, an open glass is Jesus Christ, not the rotations of. Okay, an open glass is created by rotating the curve y equals x squared defined in the domain x is in 0 to 10, 2 pi radians about the y-axis. Okay, units on the coordinate axis are defined to be in centimeters. Sure. When the glass contains... Okay, again, which part do you want me to look at? This is posted by Hey. So Hey, is there a specific part you want me to do? Can't do from B. Okay, so I guess B and C. Does it depend on A? Do I have to do A anyway? When the glass contains water to height h, find the volume V of water in terms of h. If the water in the glass evaporates at a rate of... Oh, I hate related rates so much. Okay, show that. Fine. If the glass is filled completely, how long will it take for all the water to evaporate? Okay. Are you guys allowed NSolve in an exam? I thought that that feature is removed when it's put into exam mode. Damn, okay. That's crazy. I thought I didn't, but maybe I did and I just didn't use it. I have no idea. Okay. So for this, I mean, there's some integral that you have to set up, right? Presumably. And I don't want to do calculus. I hate calculus so much. Okay. Where's the... There's probably a formula in your formula booklet for rotating stuff about an axis and getting a thingy, right? Yeah, volume of rotation. Uh, Here it is. So what do we have to do here? We have y equals x squared. I guess we probably have to rewrite this in terms of y, right? Or no, do we? Because if we're rotating about the y-axis, then rotating about the y-axis, you should use this one, right? And x squared is equal to y. So I think this one should just give you... Am I doing this wrong? This looks very suspiciously simple. And you have a to b, well, it's 0 to square root of 10, right? Or no, 0 to 100. Because it's the value of y. Of pi times y dy. That looks wrong. Yeah, x equals square root of y, but then you have to square it again, right? So that's why I'm just going straight there, because you have to do x squared and you just get this equation again. Okay. So this will be pi times x squared of, yeah, I guess that is correct. That's such a weird, okay. So pi the constant, that can come outside. Y integral will give me half y squared. So I have pi times, well, pi over 2, because I can take out the half as well, times y, oopsies, y squared, and then take it from the range 0 to 100, right? Which will then give me 5,000 times pi. Oh no, I need it in terms of h. So this is not, this will be like h squared, right? Or no, it's just h because it's the height. Okay, so this will just be pi times h squared over 2. Okay, that should be part A. This is, of course, v, right? That's the integral we're doing. So then part B, if the water in the glass evaporates at a rate of 3 centimeters cubed per hour for each centimeter squared of exposed surface area, show that. Okay. So if the water is filled to height h, that means, so okay, at y equals h, x would have to be square root of h, right? And that means, like, okay, if you have the bowl that looks like this, that's awful. And then I'm looking at this circle, right, at height h. Here, the radius is square root of h. So if I want the surface area of this, I can just use this radius to get pi r squared, but it's square root of h squared, so it should just be h. That will be the surface area over there. And so you, okay, so what you want is dv by dt. Right. Okay, got it. So you have an expression of v relating it with h. You probably have to use that to get this somehow. But you need to figure out what dh by dt is. And that's where the evaporation rate comes in. Right? So let's use this. If you do dv by dt, pi over 2 is a constant, so that can come out, times, so differentiate to h, and then this we have to multiply by dh by dt, right? And the change in height depends on this evaporation rate. So there's going to be, okay, surface area is pi times h, exposed surface area anyway. And what does it say? There's 3 centimeters, cubic centimeters per hour for each for each centimeter squared of exposed surface area. How does that give you dH by dt? Andrew is here. What are you doing in the audience? Join me. Andrew is one of the other hosts. I'm just trying to think if there's any sense in writing, like splitting up dH by dt more. I really hate related rates for this reason. It's always so finicky. I don't think that helps because that's the same formula, right? It's like that's the same thing we used to reach here. There he is. Hello.
Okay. Hello.
Hi.
I'm not gonna be here for long, but
Okay.
I'm not sure where we are at right now.
We're doing a related rates, which is my nemesis.
I know. Okay. Okay, so we did part A.
Mm-hmm.
Now we need to find the surface area of the water because we're given the rate of evaporation per centimeter squared of exposed surface area. So that's gonna give us the rate.
Yes. But how?
How do we find the exposed surface area?
So this is what I did here, right?
Okay.
It's with at height h, there's a
Yeah.
circle of radius root h, so that'll give us surface area of pi h. I guess I can write like equals a or something.
Pi r squared. Yep. Okay.
Right? So
Yep. Basically, yes. And we have dv over the. Hold up. So dv over dt. That's gonna be -3 centimeter cube per. Hold up.
wait,
Why is it the rate per surface? Oh, hold up. No, it's just dv over dA. That's not dv over
wait.
dt.
I'm
Wait,
I'm
hold up.
I'm
I'm
actually
confused.
pretty stupid. This is really simple. I'm overcomplicating this.
Oh yeah.
Yeah, because so okay. They've given you the expression here. I don't know why I did all this. Let's move this a bit. So using this, right, what they've written in words, dv by dt is going to be equal to, first of all, negative because volume is decreasing. So it'll be -3 times the surface area exposed, right? Like whatever this is. So we can write that as, well, -3 times, we know that this is pi h, but we also know h in terms of v, right? So we can use that to get h is equal to 2v over pi. That's supposed to be a pi square root. And if you plug that in here, you get minus 3 times, okay, minus 3 times pi times root 2v over pi. That should be pi, which is equal to minus 3 times 2 pi v. And that's it.
Excuse me, what? 6 marks?
I don't know why that's 6 marks. That feels...
Seriously?
I don't know.
Hold up. Hold up. Did we miss something?
I don't know. I don't know. This doesn't feel like 6 marks worth of working.
This is too good to be true.
Okay. Did everyone in the, like, do the rest of you understand what I just did? Why did I multiply by the area instead of divide? So this is essentially just following what they wrote in words, right? So 3 centimeters per hour for each centimeter squared. So if you want the total change, it'll be minus 3 times the total centimeter square area of exposed water, right? And no, so remember, they've given us a change over time, right? This is evaporation rate of 3 centimeters cubed per hour, and this is for each unit of area. So this rate of change of volume per hour is scaled by the area. That's why it's multiplied.
I'm pretty sure you already get 2, even 3 marks just from the first line there.
I guess the hidden marks were in actually figuring this out, because you
Yep,
figuring
exactly.
this out.
That's
Because
what marks are.
you should probably draw this diagram out and
True. Yeah. Okay.
that's probably where the remaining marks went. So
Yeah.
I think it makes
So
sense.
that should be maybe 2 marks. Then
Yeah.
1 mark for the negative sign.
Yeah. So then
Another one for negative 3a. Then 2 more marks. 1 mark for isolating h, and then bring it home.
yeah, I think it makes sense. Okay, let's do the
Yeah.
last question here. So if the glass filled completely, how long will it take for all the water to evaporate? Oh, that's so annoying. Okay, so you have this. I'm presumably you just need to. Okay, let's rewrite this here. So dv over dt, we got to be minus 3 times the square root of 2 pi v. And if the glass is filled completely, then we know that v will be, what, 5,000 times pi from part A. This is if it's full. And we want to presumably integrate this from 5,000 to 0, basically. Okay, hold on. Let me think. So have intervals on both sides. You get a... Yeah, you probably want to do this... Jesus Christ. It's been so long since I've solved the differential equation, which is not good as a physicist to say, but it's fine.
Come on. It's
Let's write these
separable.
down. I know it's separable, but it's just I was thinking if I'm supposed to put bounds at the start, but let's not do it that way.
Yes, I was about to say that. Yes.
So this I'm gonna write this as v to the minus 1/2 on this side. I'm taking this v over.
Yep.
So it's 1 over square root of v. So integral of 1 over v to the minus 1/2 dv. And I'm gonna keep all the constants on the other side. Oh yes, water, thank you.
Also, there's a question on can you integrate both sides? No, you cannot. Because the left-hand side has v, the right-hand side also has v.
Yeah, you have to separate them first. So that's what I'm doing here. The remaining constants are minus 3 square root
I just woke up
2 pi
and I'm gonna teach you to bed, aka in 10 minutes.
integral of, no, it's just integral of dt, right? So let's do this integral. This is, how does this work again? Minus 2 v to the 1/2, right, Andrew?
Should be positive.
But this is negative. 1 over this
Yes.
is...
So when you integrate, it's
so
gonna be 1 over 2.
Yes, you're right. See, this is why I need Andrew, man. And then this will just be t, right? And then there should be some plus c. But we know that at t equals 0, v is equal to this thing, right? So let's say this is at t equals 0, right? So let's plug that in and figure out what c is. So if t is 0, let's do this here. If v is 5,000 pi, then c will just be equal to 2 times the square root of 5,000 pi. Right? And so, okay. Now we basically plug in, we want v to go to 0. V equals 0. Solve for t. So this will go away, and we'll just get 3 root 2 pi times t is equal to... I mean, I'm almost done. 5,000.
It is 7 marks.
Square root. And so just divide
It's supposed to take a
these.
while.
I mean, the pi's cancel, right? So you should just get square root of like 5,000 over 18, whatever that is. I'm not going to simplify that. Okay. Anyway, even if the answer is wrong, which I honestly probably is because that's inevitable with related roots, I hope the method used is fine. Like once you have this, it's just a matter of seeing what kind of differential equation you have. In this case, it's separable. So you put v's on one side, t's to the other, integrate, solve.
And you should get t equals 50 over 3.
You should get what?
50 over 3. If you simplify the roots, the number works out nicely.
Oh, right. Okay. Okay. Let's go to the next question.
Oh, which one is it?
This is a...
Oh boy. Dudes.
Can everyone read that?
This is supposed to be your question of the day, people. What are you taking on? Creative. What is this?
Wait, what do you mean?
So this was one of the questions of the day. I'm pretty sure this like from 2 days ago.
Oh, come
And
on,
then
guys.
there's supposed to attempt.
Nah, I'm
And
not
now it's
doing
gonna
this,
shove it to
man.
you.
This is for you. This is for you guys to do. Don't give this to me. Especially if Andrew's the one giving it to you. So bad. So previous one had one wrong. What is the answer then? I'm not surprised that it's wrong. I hate related rates so much.
Counting.
Okay. A farmer has 6 sheep pens arranged. I'm going to zoom in. Farmer has 6 sheep pens arranged in a grid with 3 rows and 2 columns as shown in the following diagram. 5 sheep called A, B, C, D, E are to be placed in pens. Each pen is large enough to hold all the sheep. A and B are known to fight. Find the number of ways of placing the sheep in the pens in each of the following cases. So one case is each pen is large enough to contain 5 sheep. Amber and Brownie must not be placed in the same pen. And other one is each pen may only contain 1 sheep, and Brownie must not be placed in pens which share a boundary. Oh, all right. Bye, Andrew. Okay. I really like this question because, of course, I do. It's counting principles. Again, should I give you guys a chance to work this out on your own? There's 2 parts. I can do both, unless I mean they seem similar enough. I don't mind doing both. Okay. Let me zoom back out for this. Okay, I think I know how to do part A. And part B is interesting. Okay, I think I have a handle on both. So the at least for me, the important point to this question is the relation between Amber and Brownie, right? So the fact that that's the only thing that puts restrictions on the allowed configurations. And this is important for both questions. So because this is the only thing that restricts what configurations are allowed, let's consider those 2 sheep first and then figure the rest out. Okay, so let's do part A first. Each pen is large enough to contain 5 sheep. Amber and Brownie must not be placed in the same pen. So in this case, the grid configuration doesn't really matter. There's just 6 separate pens. So the only restriction is that A and B don't go in the same pen. So how many ways are there to place A and B across 6 pens where they don't share a pen? So they must be placed in different pens, right? But it can be any of the 6. So 6 permute 2 is a number of ways you can place A and B. I'm just gonna write it's like 6p2. So this is for placing A and B in their pens, right? You out of your 6 pens, you just pick 2 of them to put A and B in, and the order in this case would matter, right? Because the pens aren't the same. Then you multiply with this the placement of the other sheep, and the other sheep don't matter, right? They can go anywhere, right? Each sheep you can put in any of the 6 pens for all of the remaining sheep. So for each of the remaining sheep, there's 6 choices. Oopsies. And there's 3 sheep left, so this will just be 6 to the power of 3. Does that make sense to everyone? Okay. Help me a bit more than no, because I need to figure out where you guys are confused with this. Yeah, so the main point I was making is that the fact that Amber and Brownie are known to fight, right? This is the thing that determines, like, this is the thing that puts restrictions. Why 6 to the 3? Because, so, okay, the left side, 6 permute 2, sets the locations of A and B. But the pens are large enough to hold any number of sheep, right? So for the next step, if we're placing C, how many places are there where I can put Curly? I have 6 choices, right? Each choice gives me a new configuration. So for C, I have 6 choices. For D, I then again have 6 choices. For E, I have 6 choices. Why 6 permute 2? Because A and B they can't be in the same pen. So if I just focus on A and B alone, I have to pick 2 separate pens out of the 6. And in this case, order also matters, because if I swap the positions of A and B in the pens, it'll be a different configuration. So 6p2 is for the locations of A and B, and then for all the remaining sheep, I multiply by 6 for the 6 choices of pens. Okay, everyone on the same page? Waiting. How did I use... So in this case, the order matters. So, like, if I put A here and B here, this is like a different configuration than if I put B here and A here, right? So I have to count both. Okay, if there's still questions, just ping me and ask me. Otherwise, I will move on. So for part B, now the arrangement of these in a grid actually matters, because each pen only contains 1 sheep, but Amber and Brownie must not be placed in pens which share a boundary. So again, let's think about how to approach this. Again, Amber and Brownie are the only 2 that put a restriction on the possible configurations, right? So let's focus on where Amber and Brownie could go. So there's 6 possible places. Let's put Amber first, right? If Amber's here, then where could Brownie go? Brownie could go here, here, or here. So there's 3 choices. By symmetry, if amber was here, here, or here, each of these would also get 3 choices. So 4 times 3 gives me 12 so far. If amber was instead here, then brownie can't go here, here, or here. So there's only 2 choices. And by symmetry, same thing here, right? So for amber's placements, the number of configurations are 3, 3, 2, 2, 3, 3, which in total give me what is what is this sum? 3 plus 3 is 6, plus 2 is 8, 16? Yeah, so there's 16 configurations for where amber and brownie could be placed. It is not times 2. Be a little careful. If amber is here, then one of the configurations with brownie here is counted. But then this also counts the configuration where amber is here, and one of them involves brownie being here. So by considering all the locations of amber, you've already counted the double, like you've counted both orders already. Does that make sense? Okay, great. If instead, just as an aside, if instead you wanted to count the number of ways to pick non-adjacent squares, right, then you would find that there's 8 possible. So you could pick this, or this, or this, or etc. Like you count that, you'll get 8, but then you apply the order, you multiply by 2, you'll get 16. But both are valid, both get you the same thing. Okay, now we've placed amber and brownie, and there's 16 ways of doing that. That's before I label it A and B. Now we have to multiply this by the placement of the rest. And the rest don't have any restrictions. All we know is that there's 4 pens left for the remaining 3 sheep. So how many ways can you put 3 sheep into 4 pens? Well, it's... No. Each pen contains exactly 1 sheep, right? So you don't have 4 choices for each. You have to... Let's write this out. I have 4 pens. Permutation matters, order matters, but I have to pick 3 to put my sheep in. Okay, was that clear to everyone? I can repeat if you guys want. Okay. For the 16, actually, let me answer the other one first because it's easier. So, or quicker. So for Permute 3 just is out of, so after placing amber and brownie, there's 4 pens left and 3 sheep left. So you have to choose 3 pens to put, you have to choose 3 pens out of the 4 to put those sheep in. And in this case, order matters. So it's not combinations, it's permutations. So for Permute 3. Okay, let's explain the 16 thing again. Let's draw this. Okay, so there's 2 approaches to reach 16, and I'm going to go through both, right? First one is how many ways can I select 2 pens that don't share a boundary? So I'm going to count them out. I can pick 1, 2, 3, 4, 5, 6, 7, and 8. Right? There is 8 of them. Now, because there's 2 ways to pick 8, there's 8 ways to pick 2 pens that don't share a boundary, and A and B must be placed into these 2 pens. There's 2 options, right? I can put A and B or B and A. So in this case, I multiply by 2. So 8 times 2 will give me 16. The other option is I consider amber from the start. So say I place amber here. Then I can put brownie here, 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 right? And so for each square, I get a number of configurations. And because I'm placing them already, I don't have to multiply by 2 because the configuration's already set. And if you count up all the configurations this way, you'll get 16 directly. Does that make sense? Bridge sense? Okay, wonderful. I shall move on. Oh my, so many questions. Yeah, that's okay. Oh, more counting. Are you guys just finding counting principle questions for my sake? Because of what I said before. It's because they're hard. Fair enough. I really like them. Okay, let's go through this. So, wait, let's. Does it fit in one? Barely. Okay. In a trial examination session, a candidate at a school has to take 18 examination papers, including the physics, the chemistry paper, and the biology paper. No 2 of these 3 papers may be taken consecutively. There's no restriction on the order in which the other examination papers may be taken. Find the number of different orders in which these 18 examination papers may be taken. This is fun. Okay, let me give this a think. But what I will say is, as before, they've specified a condition for 3 of these papers, right? So that is the main thing that will restrict the actual number of configurations. Yeah, Rogue Sky, that is a perfectly valid method. I mean, one of the reasons I love counting principles so much is because there is no general strat to this. You have to always think about it and be careful. And yeah, you need to think. There's another way. There's more than one way of doing this, but I will go with what Rogue Sky said for now. So oh wait, I think I read this wrong. No, 2 of these 3 papers may be taken consecutively. So so the only restriction is oh no, I understood correct the first time. So the only one that's not allowed is all three being taken. No. What? Hold on. Yeah. Never mind. So Rogue Sky, I don't think your method works because it only removes the configurations where all three are consecutive, but the ones where two are consecutive is also not allowed. Etc. Yeah. Okay, I see. Hmm. That's like it's tough though to not overcount with that method. No, okay, I'm gonna think of a different method. Because there is a different way to do this. Okay. So I'm gonna draw out a diagram and hopefully that'll help. Okay? So there's three of these exams which have this condition. I did just drink water, but thank you. Arya. There's three of these exams that have this restriction placed on them, right? That leaves 15 exams without uh, without any restrictions. So what I'm gonna do is draw. Actually, maybe it'll be easier and faster if I type. I was gonna put a circle, but maybe I can just write write the letter O or something. One, two, three, four, five, six, seven, eight, nine, 10, 11, 12, 13, 14, 15. Right? Let's put them in a line. Right? These are your 15 non-physics math, physics, chem, biology exams. I'm going to use a stick to represent a physics, chem, bio exam. Notice how there have to be other exams in between wherever I place these three sticks, right? So for example, this is not allowed, right? So one way in which you can think about this problem is there's 15 exams and around it are 16 slots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 slots where each of those three other exams can go, such that there's always another exam between them. So the number of ways to place it here is 16 choose 3. Did that make sense? Okay. Okay. Let me explain what this diagram is again. Circles, there's 15 circles. The 15 circles there represent the exams that don't have any restrictions. There's 3 exams left to place, right? And those 3 exams can't be consecutive. So in this diagram, the vertical, like the lines, represent slots where these last exams can go, and only one exam can go in these slots. Is that clear? What I've said so far, does that make sense? Okay, great. So there's 15 exams, which creates, in some sense, 16 slots where the remaining exams can go. Just out of this restriction that they can't be consecutive. So if there's 16 slots and I need to put 3 exams in, there's 16 choose 3 configurations of slots that I can choose, right? So 16 choose 3 just gives me the configuration of where the exams will go, but I then have to multiply this by, first of all, 3 factorial for the permutations of the 3 exams, like these 3, and then multiply this by 15 factorial for the permutation of all of these exams. Okay, great. I had to take time to explain this term because this is the confusing one. Where did this come from? So once the exams are placed, there's two groups of exams, right? There's the 3 that have the restriction, and there's the 15 that don't. So in a given placement, you can then permute them because any permutation is allowed within each group. Okay, amazing. Is anyone still confused about this? Because I'm gonna move on to the next one. And thank you, Arya, for writing out the explanation. Yeah, you can. it's 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 the same thing. I was only doing it that way just for my, like, conceptually how I was thinking about it. But you're more than allowed to do that. Like this is the same thing as 16 permute 3 times 15 factorial, right? Same thing. You see the same answer. Just conceptually in my head, it makes more sense that you're finding the configuration of exam placements by group and then calculating the permutations within each group. That's why I wrote it like that. But I mean, it's whatever. You get the same answer either way, right? So the methods are equivalent. Okay, moving on. Bro, is every question gonna... I'm not complaining. I'm just kind of worried about if you guys actually want to do other topics. Okay, let's do this. This is amazing. I'm so happy. You guys don't understand. People normally just throw like nonstop calculus at me for these sessions, and this is the first time that there's been this many counting principle questions. I love this. I'm so glad you guys find calculus easy. No, we can't do Andrew. Okay, if we have time later, we can do Andrew's question of the day. Okay, let's do this. 6 marks. The barcode strings of a new product are created from 4 letters A, B, C, D and 10 digits 0 through 9. No 3 of the letters may be written consecutively in a barcode string. No 3 of the letters may be written consecutively. Okay. There's no restriction on the order in which the numbers can be written. Okay. Find the number of different barcode strings that can be created. Right. Interesting. Okay. So as before, you see that there's a general pattern here, right? The general pattern being there's a bunch of things you need to place or configure, and a small group of these have a restriction. So the question kind of signposts to you what to focus on. All right, let me think about this, and then we'll start. You guys also give this a think while I'm thinking. So 0 through 9, and then A, B, C, and D. No 3 letters, but it's possible for 2 letters to be, okay. Hmm. How many total? No. It's like, so you have the 10 digits and 4 letters, and it's just permutations of those 14 characters. Just the 4 letters, no 3 can be consecutive. Yeah, it's. I had the same confusion you did because I thought we had to repeat these for a number of barcode digits, but no, it's just like that's all the. These are all the symbols we have. We have to put them all in a certain order, but there's a restriction on that. Yeah, 14 characters, right? Like 10 digits plus 4 letters. There's 14 symbols you're manipulating here. I'm surprised that this is 6 marks. I don't have a simple way of doing this one. Okay, what I'm gonna say, because I feel like a lot of you guys really like the the approach of getting all the permutations, so 14 factorial, and then subtracting the ones that don't obey the restriction. The trouble with this, like this, it is a valid approach in a lot of cases, but the trouble with this is that you're really prone to overcounting. So you have to be very careful. So in this case, you might think, okay, maybe I do 14 factorial and then I subtract all of the configurations with 4 4 in a row, and then also subtract all the configurations with 3 in a row. But you have to be very careful how you count the ones with 3 in a row, because you can't ignore the last one. You can't ignore the 4th one. One way, yes, water. Thank you. So what I mean by this is, like, say your string starts with A, B, C, D, and then some numbers, I don't know, 2, 4, well, whatever, right? If I'm counting the permutations where there's 4 in a row, this will give me 1 count, right? So I can subtract this and it's gone. Don't worry about this. I'm gonna upload this file to the Math AA channel once I'm done, so you'll have access to this. Don't worry about the screenshots and stuff for now. Okay, so for 4 in a row, you'll count this and you'll subtract it. Now, when you start counting for 3 in a row, you have to be really careful that this doesn't get counted. Because think about it, right? There's 3 in a row over here. So you have to be careful that, okay, if there is 3 in a row, it shouldn't also have the 4th one nearby. Because if you just naively count 3 in a row as well, you're going to count this thrice, right? You're going to count this one, and you're going to count this one. So you have to be very, very, very careful when subtracting the permutations you don't want. So that's why I would advise against this approach. So as before, what I'm going to do is create, again, this problem is very similar to this last one, where there's 4 members which have restrictions and 10 that don't. And the restriction is essentially that they can't, it's about to do with how consecutive they can be. So as before, I'm going to create, the 10 digits don't have any restrictions, right? So I'm going to create 10 slots again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, for fuck's sake. Dude. 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And now let's think about this. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 slots, right? This is the same as before. But for this problem, you are allowed to have 2 letters in a row. Why 10 and not 14? Because, so the letters are the thing that have restrictions, right? There's something about letters not being able to be written consecutively for too long. The 10 digits don't have any restrictions. So they are sort of like, they have to go in between the slots where the letters can go. So that's why I have put it in this setup. So there's 11 slots where the letters can go, and there's restrictions on how you can place them. So now let's think about this. Each slot can contain at most 2 letters, right? This is different from before. In the last question, each slot could contain only 1 of the 3 exams with the restriction. In this case, the slots could contain 2 letters. So we have a couple of cases to go through. Case number 1, there's 4 slots to fill, each with 1 letter, right? This is case number 1. I mean, it doesn't have to be case number 1. I'm just numbering them for your sake. Case number 2, the first slot has 2, and the other 2 have 1, and there's 3 slots to fill using these. Now, the order of this barcode matters, right? So this second case actually spawns 2 more cases, right? The third case is where the first one has 1, second one has 2, third one has this, and the fourth case is where this, and this, right? And then there's 1 more case that's possible, And that's where you have two groups of two. This is it. That's all of them, right? Any other grouping will give you 3 or more. Is everyone with me so far? Great. So for each of these 5 cases, I have to use these to fill in the 11 slots that I have. Each one will give me a valid barcode configuration of letters and numbers, which I then multiply by 4 factorial and 10 factorial. Yeah, but remember, I'm not worrying about permutations yet. So multiplying by 4 factorial and 10 factorial will come at the very end. For now, I'm just counting the ways in which these two groups can be configured. And no rogue sky, because there's a difference between the ordering of where the slots are and the ordering of the letters that occupy the slots. So, for example, I could have the order A, B, C, D going across 2, but that'll be a different order from the A, B, C, D going across 3, because where the A, B, C, Ds are is different now. So I have to count both. Yeah, like, so essentially the difference between these is like, say I have a barcode sequence that goes like 2, A, B, 3, C, 4, D, etc. Right? That I could get this from 2, and then from 3 I could have like 2, A, 3, B, C, 4, D, etc. Right? So these, for each of these, there's 4 letter slots, right? So I could have the 4 factorial permutations, but there's still a different barcode. So I have to consider both. Okay, great. I'm going to remove this because I have to do some working, like math working out here. Delete. Okay. So let's calculate this one by one. There's always 11 slots. So this will give me 11 choose 4, right? This one, actually all of these, because there's only 3, right? This will give me 11 choose 3. Oh, oops. 11 choose 3, 11 choose 3. And then this one will give me 11 choose 2, right? For C, order doesn't matter. Order will matter for this question, but in this case, I'm only choosing which slots are taken up, but not in which order they're being taken up. So in total, I'm just going to add all of these up, and that'll give me the total number of ways in which the letters and numbers can be arranged. So total number of configurations for this is 11 choose 4 plus 3 times 11 choose 3 plus 11 choose 2. Now, I multiply this by the permutations within each group. So I can multiply this by 4 factorial for the letters, and then multiply this by 10 factorial for the numbers. I also feel like there's a simpler way of doing this, because it's suspicious that it's 6 marks, but this is the best I could come up with. To be honest, so remember the method I was talking about to be careful with, where you start with 14 factorial and you remove the bad orderings, like the orderings that don't obey. It's 3 times 11 C3, yes. We're multiplying by 4 factorial and 10 factorial because we split this into 2 groups, right? There's a group of letters, which is 4, and there's a group of numbers, which is 10. So once you have the configuration of letters and numbers, within each group, you need the factorials as well. Now, I'm gonna do an aside here. Let's consider the cases where the restriction is broken, but within the same framework. Okay? So within the same framework, there's three possibilities. I'm gonna actually copy this diagram down here. There's three possibilities which break the restriction. So one is that I could have three in a row and then one somewhere else. And actually, this gives me another one, right? Because the order in which they appear matter. So I can have 3, 1 or 1, 3. Or I can have all four bunched up. Right? Same formula as before, but it just difference being this time, this tells me what to avoid, right? So this will give me 11, choose 2. This will also give me 11, choose 2. And this will give me 11, choose 1. Now, again, this is all the ones to avoid. So when calculating the total, I do 14 factorial minus the configurations that this gives me. So this will be 2 times 11, choose 2, plus 11, choose 1, times 4 factorial times 10 factorial. Okay, both of these will give you the same answer. But this is what I meant by you have to be careful about removing the cases that break the restriction. You have to be really careful to not overcount. Okay, any questions? Can explain. Yes, it is a 3 times 11 C3. It's because I'm adding all of these up. I'm adding these up. So it's 1 11 C4, 3 11 C3, and 1 11 C2. So that's what I've done here. Can I send the full question? This is the full question, sorry. You can take a read and hopefully it makes some sense, some semblance of reasoning through what I'm doing. Okay. Anyway, I'm gonna move on now. So let me grab the next question. And if you have questions about previous things, just again ping me and tell me what you are confused about. Or if you want me to go over something again, that's also totally okay. Nope, that's the same question as this one. Okay. More permutations and stuff. Let's put this here. And let's zoom in. Okay. Cool. 7 marks. A group of 10 children includes one pair of brothers, Alvin and A and B, and one pair of sisters, C and D. The children are to be seated at 10 desks, which are arranged in 2 rows of 5, as shown in the following diagram. Alvin and Bobby must be seated next to each other in the same row. Find the number of ways that the children can be seated. Okay. So A and B has a restriction, C and D don't. What even is this question? Okay. This is such a weird premise of a question. Whoa, yeah, water, thank you. Okay, and then after an argument, C and D can't be seated next to each other. Find the total number of ways. All right. All right. Let me think. So I mean, I'm guessing next to each other. Because so A and B must not be seated next to must be seated next to each other in the same row. So I'm guessing next to each other in the same column also counts for part B. So that will be a little tricky. But anyway. Okay, I think I get how to do A. I think I get how to do B. I think. Wait. Yeah, it's just a bit odd. There's just a lot of counting to do. I wonder if there's a better way to approach B, but it's quite weird. Okay, let's get to it. So for A, so this question is actually similar to the this one, the sheeps in pens. So I'll be treating it somewhat similarly to that. So as before, we have been given a restriction with A and B. So A and B must be seated next to each other in the same row. There's no restriction on anything else. So you might as well figure out the configuration of A and B and then figure out everything else. So if A and B have to sit next to each other, there's only a couple ways in which this could happen, right? They have to be in the same row and next to each other. So that's one, that's one, that's one, that's one. There's 4 in the top row. There's another 4 in the bottom row. So there's 8 total desk configurations that they can take up. And then the order of A and B is like it can be A and B or B and A for each one. So it'll be 8 times 2. I'll write that here. 8 times 2 ways in which A and B can be placed. And this is just for A. I'll write A, B. And then there's no restriction on anything else, right? So there's 8 students left. They can be in whatever permutation. So you multiply this by 8 factorial, right? So that should be it for part A. And it's simple enough because it's 3 marks, right? That's yeah, there's no restriction on the remaining 8 students, so that's it. That's all you worry about. Part B, I'm really wary because I don't see an elegant way of doing it. But let's draw out what I've thought of. So let's say that A and B are here. Now, what we can do is count the ways in which C and D are placed. So remember back here when I was counting the ways in which A and B could be placed without being adjacent? This is really similar to that, right? So if C is here, where are the places that D could be? There's 1, 2, 3, 4, 5, 6, right? If C is here, then where can D be? There's 1, 2, 3, 4, 5 that are not adjacent, and so on. Here it's 1, 2, 3, 4, and so I could just count this out for each square. So here it was what, 6? Here it's 5. Here it's 4. If C is here, then I'll have 1, 2, 3, 4, 5. If C is here, then I have 1, 2, 3, 4. If C is here, then 1, 2, 3, 4. C is here, then I have 5, these 5, right? And then if C is here, I have these 5. So sorry, I should have read the context out. So after an argument, C and D must not be seated next to each other. A and B must still be seated next to each other. So find the total number of ways now. So what I'm doing is for each configuration of A and B, so let's consider the one in the corner. These are the number of ways. If C is sitting here, this is the number of ways that D can be placed, right? And then in total, that gives me something. So in this case, if I add up, what is this, 20, 30, 38? Yeah, but like, I think we have to just keep doing this because I don't see a clean way of figuring this out. So if I copy this out now, and instead we consider it from here, right? We have to just do this game again. So if C is here, 6, 5, 5, 5, 5, 4, 5, 5, right? And this will give me 10, 20, 30, 40. 40 configurations? Okay. Is anyone lost? Because I went really fast there. So I'm going to stop here. Does anyone have no idea what I'm doing? Okay. Okay. For those of you that are lost, do you understand why I have circled 2 squares? Like why I have put a rectangle around 2 squares? Do you understand what that represents? Yeah, okay. So that's where A and B are placed because they need to sit next to each other in the same row. So what I'm doing is I'm considering a particular case of A and B. So let's say they're at the top left corner, right? That's the first set. If they are at the top left corner, there are only certain configurations where C and D can now sit given this restriction. So C and D cannot sit next to each other, which means if A and B are here, there's this configuration of seats available for C and D, but we have to count how many there are where they can't sit next to each other. So what I did is, let's say C is here. If C is sitting here, D cannot be sitting here, right? Because it's adjacent. So how many seats are left that are valid configurations? where D can be placed? Well, there's these 6, right? These 6 options are available. So I put a 6 in that cell and then moved on. So if C is instead here, it can't be here, it can't be here. D has 5 options for a valid seeding. And I'm just going through each place where C could sit, seeing how many valid configurations D has. And this gives me the total number of configurations of C and D being placed for a given configuration of A and B. Everyone with me now? Great. So for the top one, there's 38. In the next case, there's 40. And you just keep doing this, and it'll give you all of them, right? I think they can't be placed adjacent in different rows, because this one says seated next to each other in the same row. So I think in the same column still counts as adjacent. Now, I'm going to pause here and say something really slowly. There's some symmetry here, right? If I reflect this image horizontally and vertically, then you should get the same numbers. So yes, also 4. Good. So remember how we said there was 8 configurations and then this 2 was for permutations, right? So for the 8 configurations, 4 are reflections of this and 4 are reflections of this. So I can just multiply these by 4, and this gives me the total number of placements of A, B, C, D that are valid. So let's do this. 38 times 4 plus 40 times 4. This gives me in total the number of placements of AB, the number of placements of CD that keep that don't break the restrictions we were given. Now, we also need to consider permutation, right? Because this is just the configuration without caring where they're placed. This is just placing the groups of AB, the groups of CD, and the groups of the remaining 6. So for AB, there's 2 factorial. Then for CD, there's another 2 factorial. Actually, no, sorry. The permutation of C and D are already taken into account. Actually, what I should do is over here, each seat has a... Sorry, let me go back. That's not good. Let's do it like this. Each of these actually has 2, right? Because it's AB or BA. So let's calculate let's incorporate that into this. So it's actually times 8. There's 4 reflections and 2 permutations. So we have 38 times 8 plus 40 times 8. This is how many ways to place A, B, C, and D, including permutations. Yes, I know. I think I'll wrap up soon. I think there's like one question left or something. So I'll do that one and then end the session. So this is for A, B, C, and D, right? Now I multiply this. There's 6 students left and there's no restrictions left. So this should just be times the 6 factorial. No, I'm not getting paid for this. I'm doing this because it's fun. 6 factorial because there's 6 students left and there's no restrictions, so you just count all the permutations of the remaining 6. Okay. Yeah, I was just getting it. So it's a vectors question that's left.